Today's notes on Unit 4, Section 4, we're going to be discussing gas law stoichiometry. Gas law stoichiometry involves two different calculations. If we are at standard temperature and pressure, we can use our molar volume, 22.4 liters. If we're not at standard temperature and pressure, we need to use the ideal gas law, PV equals nRT. You can solve any gas stoichiometry problem using three simple steps. First, make sure you have a balanced chemical equation. 2, identify what is given to you in the problem and what the problem asks you to solve for. And 3, use your stoichiometry roadmap to find the unit you're starting with and the unit you need to end with. To our stoichiometry roadmap, we're going to be adding liters of A not at STP. So use the equation to solve for N to get to moles of A. Then use your mole ratio to go back and forth between moles of A and moles of B. And then finally use your ideal gas law equation again to solve for the unknown pressure, volume, or temperature. Let's try example 1. First, make sure your equation is balanced. Then figure out where we're starting. So we're starting with 50 grams of magnesium. We're going to be using our molar mass first. Then we're going to use our mole ratio. And finally, we need to get to liters of B. And this time we can go to STP. So we're going to be using 22.4 liters to convert. Let's try example 2. First, make sure you have a balanced chemical equation. Then let's figure out where we're starting. We have 4 moles of gasoline. We're starting at moles of A. Then we want to use our mole ratio to get to moles of B, and then finally get to liters of oxygen. We'll have to use the ideal gas law because we're not at standard temperature and pressure. Let's try example 3. So first we want to figure out where we're starting. We are given 20 liters of oxygen gas. We're starting at liters of A, not at STP. So we need to use the ideal gas law first to solve for moles. Then we're going to use our mole ratio to get to moles of water. And then finally we want to use our molar mass to get to the mass of water. We can calculate the density of a gas using our ideal gas law equation if we rearrange it. This equation, D, stands for density in grams per liter, M is the molar mass of our gas, P, pressure in ATMs or torr, R, our gas law constant, and finally T, temperature in kelvins. Let's try example number 4. A sample of CO2 has a density of 10.3 grams per liter at 5.25 ATMs and 273 Kelvin. What is the molar mass of the gas? First step is we want to rearrange our equation to solve for M. First, we're going to multiply by RT and then divide by P. For example number 5, we're asked to find the density, so our equation is already set up to solve. For example number 6, we are given the density of a gas at STP, and our goal is to find its identity. The way we can identify a gas is by its molar mass. So for this problem, we want to solve for the molar mass of our gas and compare it to the molar mass of the elements on the periodic table. The last equations for our gas laws include Dalton's laws of partial pressure. The first equation tells us how to calculate the total pressure of a mixture of gases by simply adding together the individual partial pressures. To find the partial pressure of a gas, we take the mole fraction times the total pressure. For example 7, we have a mixture of CO2, oxygen, and nitrogen gases, and our goal is to find the total pressure. We need to use the first form of Dalton's law. For example number 8, we are asked to find the partial pressure of each of the gases in our mixture. We need to find the partial pressure of nitrogen and the partial pressure of oxygen. We will be using the second equation from Dalton and then also our mole fraction equation from our last section. Let's first figure out the mole fractions for both nitrogen and oxygen. We're going to take their moles divided by the total moles. Now that we have the mole fractions for both nitrogen and oxygen, let's calculate their partial pressures, making sure we use the total pressure given to us in the problem. The kinetic theory of gases describes how gases behave. First, gases are composed of separate teeny molecules. 2, they are in constant random motion. 3, their collisions between one another result in no loss of energy, meaning they are elastic. And 4, they have no attraction to one another. Maxwell distribution charts show us how molecules are moving. On our x-axis, we have the speed of the molecule. On the y-axis, we have the number of molecules. The peaks on each of these curves show us where the average molecular speed of the molecules are. Looking at this distribution chart, we have oxygen at 2 different temperatures, one at 25 degrees Celsius and one at 1000. We can see that as temperature increases, the average speed of the gas particles increase. Oxygen at 25 degrees Celsius has a speed of about 500, while the other one has a speed of about 800. Lastly, we use these graphs to compare gases of different masses. We have 4 gases ranging in mass from 4 to 132. We see that as the mass of the gas increases, the speed of the particles go down. Helium being the lightest travels the fastest, and xenon being the heaviest travels the slowest.